All right, for number 8, we're going to construct and simplify the difference quotient. And the difference quotient says to take your function, and wherever there's an x, you're going to substitute in an x plus h, and then you're going to subtract off your function untouched with nothing plugged in. So your function is going to be actually in the problem twice. First with an x plus h subbed in, and then just regular as it originally started. Okay, so let's go ahead and do that. I'm going to get my function ready to plug in an x plus h. My function is 3x squared plus 2 times x minus 4. And then I'm going to subtract off my regular function as is, which is 3x squared plus 2x minus 4. And that whole thing's going to end up being, whoops, and that whole thing's going to end up being over h. And then in for each of these x's that used to be there in my function, I'm now going to put in an x plus h. And then we're ready to start simplifying. Okay, so x plus h squared means that I have to FOIL that out. And when you FOIL x plus h squared, you are going to get x squared plus 2xh plus h squared. And then I'm going to distribute my 2, and I get 2x plus 2h. And I'm just going to carry down my negative 4. And this minus sign right here still needs to be distributed. You get negative 3x squared minus 2x plus 4, and that is all over h. Now, I did not FOIL this out the long way because it's going to take up a lot of room over here. So I'm just going to show it to you off to the side if you need to see what it looks like. X plus h squared would be x times x, which is x squared. And then x times h is xh. Another x times h for my inners and my last is h squared. And then these two guys in the middle combine, your inners and your outers combine together because they're like terms. They have the same variable ending. 1xh plus 1xh is 2xh, and then that's it. So once you FOIL x plus h out a whole bunch of times, then you probably already know what it's going to come out to be, and you can just like do that in your head like I did over here. It'll save a little bit of space, and you won't have to recopy things down an extra time or two. Okay, so some things are going to cancel out right away, and I'm going to get rid of them now instead of waiting till later. I can do 2x minus 2x to give me 0, and I can do negative 4 plus 4 to give me 0, and that wipes out a couple terms in one shot. Over here, I'm going to distribute my 3, and I get 3x squared plus 6xh plus 3h squared. And then I'm going to bring down my 2h minus 3x squared. That's all over h. And I see something else that can cancel out now that I distributed that 3. I have a 3x squared in the front and a negative 3x squared in the back, and they are going to cancel out. And that leaves me with 6xh plus 3h squared plus 2h over h. And I'm going to factor out an h out of my numerator, and I'm left with 6x plus 3h plus 2 all over h, and then I get to cancel my h's out, and my final answer is going to be 6x plus 3h plus 2, and that's it. Okay, for number 9, we are going to find the composition of f of g of x and g of f of x. Let's start with f of g of x first, and f of g of x is equal to f with g of x subbed inside for all of his x's. And I'm going to get f of x ready to go. F of x is 2x squared minus x minus 2. The two x's that were there now have parentheses ready to sub in g, and g is 2x minus 1. So for each of those parentheses, I'm going to put in a 2x minus 1. And then you can go ahead and FOIL out 2x minus 1 squared. You get 2x minus 1 times 2x minus 1. And then I'm going to distribute right away before I start to FOIL my negative sign, and I get negative 2x plus 1 minus 2. And then let's start FOILing. I get 4x squared minus 2x is negative 4x plus 1. And then minus 2x. I'm going to combine the 1 and the minus 2 to get negative 1. Let's distribute our 2. I get 8x squared minus 8x plus 2 minus 2x minus 1, and then combine like terms. You have 8x squared minus 10x, and then plus 1. And then that's it. And you don't have to find the domain of your composite function in this problem, but if you were to find the domain, it would just be all real numbers. The domain of your composite function on that first line is all real numbers, and the inner function's domain is also all real numbers. So that's it. The intersection between those two things is all real numbers. All right, let's go ahead and find g of f of negative 2, and that is equal to g with f of negative 2 subbed in. I'm going to do f of negative 2 all by itself. You can do the notation differently if you want to, but I like to separate the problem into two steps. So I'm going to take 2 times negative 2 squared minus, minus a negative 2, and then minus 2. And then I get 2 times positive 4 plus 2 minus 2. Those two 2's cancel out, and I get 8. That is not the final answer, because now that you get f of negative 2 calculating out to 8, you now have to do g of 8. And then g of 8 is equal to 2 times 8 minus 1, and 16 minus 1 is 15, and that is actually the final answer down here. Okay, you don't get two answers. It is a single answer at the end. All right, so let's go ahead and find f of g of x for number 10, and then we are going to find the domain. So we are doing f of g of x, which is f with g of x plugged inside of it, subbed inside for all its x's. F of x is 5 over x, and in for that x.
If you chew this stuff, it turns into gum.
Oh.
So it's called gum pop rocks.
So we are getting f ready to substitute in g. F is 5 over x, and in for that x we're putting in g, which is the square root of x plus 1 minus 4. And then if I were to clean that up, I would just remove parentheses, and you would have the square root of x plus 1 minus 4, just like that. And then the domain is going to be the domain of my composite function, and then including any domain restrictions from the inner function, which was g of x. So my composite function has this fraction now, and I need to figure out what makes the denominator equal to 0 under this fraction bar that I'm highlighting over. That whole entire denominator, I have to figure out what makes that whole thing equal to 0. So I take my square root of x plus 1 minus 4, set it equal to 0, and I solve it. That is the domain of the composite function.
Oops.
That's okay, Ellie. I'll get it later. So I'm going to add 4 to both sides. I get the square root of x plus 1 is equal to 4. I square both sides to get rid of my root symbol. I'm going to square the left side. It's going to clean off that root. What you do to one side, do to the other. And then x plus 1 drops down. The root symbol is gone. The right side I get 16, and then I have x is equal to 15, but that's technically what x cannot equal. So far, the domain of my composite function, before I simplify it, not that there was anything to simplify, is that x cannot equal 15. What did I do just there? X cannot equal 15. Now we also have to bring in any domain restrictions from the inner function. And my inner function is g of x. And underneath this radical symbol all by itself, that cannot be a negative number. It has to be a non-negative number. And non-negative numbers are greater than or equal to 0. So I take my x plus 1 and figure out what makes it non-negative or greater than or equal to 0 by setting it greater than or equal to 0. And then I subtract 1 from both sides. X has to be greater than or equal to negative 1. So my negative 1 is here, and x has to be greater than that. Now we want the intersection of these two domains. We want to figure out where they overlap, and they're both shaded at the same place at the same time. So if I look over here where I'm boxing off, each one of my graphs is shaded there. When I look at the middle where 15 is, they're both not shaded. There's a hole in the top graph that is not an intersection of domains. And then this guy right here, to the right side, all of that they have in common. So the domain, if I merge those two together, goes from negative 1 and cruises on up to that 15. And then it skips over 15 because you can't have x equal 15. And then from 15 onward, it's all shaded in for both. My domain goes from negative 1 to 15, unioned with 15 to infinity.